Welcome to GNANA DEEKSHA, concept-based digital learning. I am Dr.Sumathi Natarajan, lecturer in microbiology at Telangana Social Welfare Residential Degree College for Women, Mahindra Hills. In today's session, we will learn about an essential tool in microbiology, the microscope. The discovery of microscope is a major milestone in the field of science and has enabled mankind to study the ever-fascinating world of microorganisms called microbiology. Today, we will learn how microscopes were invented, what are the different principles that govern the working of microscopes, and how they can be applied for better imaging. We will also look at what are the different types of light microscopes and electron microscopes. Finally, a little information on the advancements made in the field of microscopy. Before we start off, I am sure many of you might have used a magnifying glass to see something that you can't see with your naked eye. Today's microscopes just use two such magnifying lenses to help us see the objects invisible to our naked eyes. A microscope is thus an instrument that is used to magnify small objects. Microscopes are an indispensable tool in educational institutions, various industries, and scientific laboratories. They can be used to view anything from living to non-living. We can see cells, tissues, organs, and all the different types of microorganisms like bacteria, fungi, algae, protozoa, and also viruses with microscopes, as well as microscopes are also used to see and study non-living things like the surface of polymers, ceramics, glass, soil particles, and microchips. Depending on the number of lenses present, there are two main types of microscopes: simple microscope and compound microscope. Simple microscope consists of a single lens. Since olden days, apart from biologists, these microscopes were commonly used by jewelers and watchmen. Such self-made simple microscope was also used by the famous Antony von Leeuwenhoek to discover microorganisms. The compound microscopes, on the other hand, consist of two or more than two lenses. These microscopes are more popular in use as they provide a higher magnification. The history of microscopes dates back to late 15th century when the first compound microscope was invented by Dutch spectacle makers, the father and son duo named Hans and Zacharias Janssen. In 1630, Giovanni Faber coined the term microscope after he observed the compound microscope created by Galileo Galilei. In 1667, Robert Hooke, in his famous book, The Micrographia, described observing honeycomb-like structures in a section of cork using his compound microscope. He called these structures as cells. In 1676, Antony von Leeuwenhoek, a Dutch cloth merchant who had a hobby of grinding glass, was able to observe protozoa and bacteria, which he called as animalcules. His simple microscope was capable of magnifying 275 times, and he is rightly called the father of microbiology. As technology improved in the 18th century, microscopy became more popular among scientists. Joseph Jackson Lister eliminated certain chromatic and spherical aberrations by combining lenses that greatly improved image resolution, whereas Kohler worked on providing an even illumination for specimens observed under microscope. Finally, Ernst Abbe gave a mathematical formula correlating dissolving power to the wavelength of light, which laid a foundation for the invention of the modern light compound microscope. In 1931, Ernst Ruska and Max Knoll designed and built the first electron microscope, which depended on electrons and not light to view an object. Fritz Zielinski developed phase contrast microscope that allows the imaging of transparent samples like cells by using interference rather than absorption of light. The 19th century thus witnessed a bloom of advancements made in the field of microscopy. When we look into the working principle of light compound microscope, it is generally consisting of two convex lenses. One is the objective lens that is located close to the specimen. Other is the ocular lens, that is the eyepiece, which is present near to our eye. When light falls on the specimen or object, the objective lens first produces a real and inverted image. This image now acts as an object for the ocular lens, which finally produces a magnified and virtual image for our eye to view. There are two main factors that govern the efficient use of microscopes: the resolving power and the numerical aperture of objective lens. The resolving power of an objective lens is simply its ability to differentiate two lines or points in an object. For example, if we see two dots using a microscope and the dots are very close to each other, the ability of the microscope to display them as separate dots is called as resolving power. Our eye has a resolution or resolving power of 0.2 mm, which means it can differentiate between two lines or objects that are separated by a distance of 0.2 mm. Objects that are close together by less than 0.2 mm cannot be separated and will appear as one object to our eye. The light compound microscopes have a resolving power of 0.2 micrometer, and the highest resolving power achieved is with transmission electron microscope, which can distinguish objects separated by a distance of 1 nanometer. Hence, this microscope is used to view internal cell structures. The resolving power in turn is dependent on the numerical aperture of the objective lens. It is a measure of the light gathering ability of the lens. Numerical aperture takes into account two things. One is the refractive index of the medium that is present between the specimen and the objective lens. Other is the angle subtended by the cone of light onto the objective lens. You all should be knowing that refraction is the bending of light rays. When light passes from one medium to another in microscope, there is refraction of light. The refraction of light in microscopes takes place when light passes from the glass slide through the specimen cover slip into the air and then again into the objective lens. A greater refraction may result in a blurred image. To avoid this, immersion oil is used at higher magnification of objective lenses. The refractive index of air is 1, whereas refractive index of oil is 1.518. which is close to the refractive index of glass, that is 1.56. Thus, when viewing specimen with 100x objective lens, oil immersion is used so that refraction of light is reduced and the image is clear. The working distance is the distance between the specimen and the objective lens. As we can see in the image, greater is the working distance, smaller is the angle that is subtended on the objective lens, and smaller is the numerical aperture. As the working distance decreases, the angle is going to increase. The numerical aperture will also increase. The numerical aperture and resolving power are related by this equation. The resolving power is thus directly proportional to the numerical aperture and inversely proportional to the wavelength of light that is used for illumination. With these in mind, let's go through the different types of microscopes. Based on the source of illumination and magnification, microscopes can be broadly categorized as light microscopes and electron microscopes. Light microscopes use light as a source of illumination and can be considered under the following types: bright field, dark field, fluorescence, phase contrast, differential interference contrast, and confocal microscopes. Electron microscopes, on the other hand, use electrons for illumination and are mainly classified as transmission electron microscope and scanning electron microscope. Bright field microscope is what we routinely use in our college labs. The base of microscope consists of a plano-concave mirror which is used to gather natural light. The beam of light is then focused by a condenser lens onto the specimen which is placed on the stage. An iris diaphragm is present just below the stage that allows the user to adjust the amount of light projected upward onto the specimen. The objective lens picks up the light transmitted by the specimen and creates a magnified image of the specimen inside the body tube. This image is again further magnified by the ocular lens or eyepiece. In order to see the specimen clearly, the focal length is generally adjusted with coarse and fine adjustment knobs that are available in the microscope. The objective lenses are mounted onto a revolving nose piece. Commonly used objective lenses are 4x, also called as scan power, 10x or low power, 40x or high power, and 100x, which is also known as the oil immersion lens. We can see that when the objective lens is changed from low to high power, the image is magnified so many times and minor details become clearly visible. The total magnification is obtained by multiplying the power of objective lens and ocular lens. The maximum magnification achievable with bright field microscope is 2000 to 3000 times. The image produced by a light microscope is generally darker against a bright background. Staining is generally necessary to enhance and create contrast in the specimens that are observed by bright field microscope. I am sure we all will agree that we can see the stars clearly in the night sky. Similarly, our next type of microscopy called dark field microscopy, where specimens observed are bright against a dark background. There is no need to stain and the specimen can be observed in its live native state. The dark field microscope makes use of a dark field stop or light stop in the condenser. The stop blocks all light from entering the objective lens except the peripheral light that is reflected off the sides of the specimen. The resulting image is a brightly illuminated specimen surrounded by a dark or black field. The dark field microscopy is ideal for viewing specimens that are unstained, transparent and absorb little or no light. It is used for observing live and unstained biological samples. It is used in the routine diagnosis of syphilis, a disease caused by the spirochete Treponema pallidum. Let's now learn about a more advanced type of light microscope, the phase contrast microscope invented by Fritz Zenck. The phase contrast microscope converts phase shifts in light passing through a transparent specimen to brightness changes in the image. The principle is based on the wave nature of light and the fact that light rays can be in phase or out of phase. As seen here, if wave peak of light rays from one source coincide with the wave peak of light rays from another source, the rays interact to produce reinforcement or constructive interference and relative brightness. However, if wave peak from one source coincides with the wave trough from another source, the waves interact to produce destructive interference or relative darkness. The phase contrast microscope makes use of a condenser annulus or annular diaphragm that projects a hollow cone of light onto the specimen. There is a phase plate in the back focal plane of the objective lens that enhances the phase difference by retarding the diffracted waves. In phase contrast microscope, one set of light rays come directly from the light source and are called the direct rays or undiffracted rays. The other set comes from light source, that is reflected or diffracted from a particular structure in the specimen. The diffracted light passes through the light retarding portion of the phase plate and is retarded further by a quarter of a wavelength. When the two sets of light rays, direct and the diffracted rays, are brought together finally, they form an image of the specimen containing areas that are relatively light through shades of grey to black. Here we can see an example where the diffracted ray is actually retarded further after passing through the phase plate. This ultimately generates contrast in the image when the direct and diffracted rays are combined. As seen in the image, the phase difference of light will vary as light passes through different areas and organelles of a cell. Thus, the phase contrast microscopy, the internal structures of a cell become more evident. The major advantage of this microscope is live specimens can be viewed in their natural state and high contrast images are produced. A better alternative to phase contrast microscope is the differential interference contrast microscope that was invented by Nomansky. In this microscope, light is first polarized after passing through a polarizer so that the light waves oscillate in only one plane. Next, this light beam passes through a two-layered modified Wollstonecraft prism to be split into two beams. The path of one beam is directed through the specimen and the other, called as the reference beam, passes through the background. The two beams are again combined by an upper Wollstonecraft prism placed above the objective lens. Differences in the refractive indices in the specimen are visualized as differences in brightness in the final image. One advantage of DIC over the phase contrast microscope is the absence of the hollow surrounding the periphery of the specimen. Next, let us learn about yet another type of microscopy, the fluorescence microscopy. Fluorescence microscopy takes advantage of the phenomenon of fluorescence, which is the ability of certain molecules called fluorochromes to absorb a light of shorter wavelength, get excited from the ground state to the high energy level and emit light of a longer wavelength as it returns back to the ground state. The specimen to be viewed with a fluorescence microscope is generally stained with a fluorochrome dye. For example, in the image shown here, the fluorochrome is excited by blue light and it emits green light. A fluorescence microscope generally consists of a mercury arc lamp or halogen lamp as the light source. The visible light consisting of all the colors of VIBGYOR then pass through an excitation filter. Here you can see only the blue light is allowed to pass through this filter, whereas all other colors are blocked as the fluorochrome is excited by the blue light. A dichroic mirror which reflects the blue light but allows only the green light is used on the path of the blue light. The mirror is fixed at such an angle that the blue light is reflected downward to the specimen. The portions of the specimen which are stained with the fluorescent dye absorb the blue light and emit green light. Only the green light goes upward and passes through the dichroic mirror and the excitation filter. Our eye perceives the stained portions of the specimen as glowing green object against a jet black background, whereas the unstained portions of the specimen remain invisible. Here are a few images of cells stained with different fluorochromes and as observed under a fluorescence microscope. The invention of electron microscopes revolutionized the field of microscopy and helped overcome the limitations of light microscope. An electron microscope uses accelerated electrons as a source of illumination. Let's recall that resolving power is inversely proportional to wavelength, which means resolving power increases with decreasing wavelength of light. The wavelength of an electron can be up to 1 lakh times shorter than that of visible light photons, thus making electron microscope that is having a very high resolving power and can reveal the internal structures of cells. Instead of using glass lenses, electron microscopes use electromagnetic lenses to focus a beam of electrons onto a specimen. There are two main types of electron microscopes. The transmission electron microscope or TEM, that is used to view the internal cell structures of specimen, and scanning electron microscope or SEM, that is used to study the surface of specimens. In transmission electron microscopes, a heated tungsten filament in the electron gun generates a high velocity beam of electrons that travels in a vacuum tube. This beam of electrons is focused by a series of electromagnetic lenses that are analogous to the condenser, objective and eyepiece lenses of the light microscope. The object or specimen is placed on a copper mesh grid between the condenser and objective lens. The specimen scatters electrons passing through it, and the electrons leaving the specimen reaches the objective lens to form an image that is further magnified by projector lens, and the final image is formed on the fluorescent screen or on a photographic film. The final image shows many light and dark areas depending on the number of electrons absorbed by the different areas of the specimen. For example, a denser region in the specimen appears dark as it absorbs more electrons, since fewer electrons will reach the projector lens and the screen. However, transparent regions are more brighter. Contrast is greatly enhanced by using heavy metal stains like lead citrate or uranyl acetate that absorb electrons. The scanning electron microscope's lens system, in addition, it contains scanning coils or deflection coils that are placed perpendicular to the electron beam. These are used to raster the beam onto the sample. The interaction of electron beam with the sample can generate many different types of electrons. The two types of electrons that are actually used for imaging are the backscattered electrons and secondary electrons. Backscattered electrons belong to the primary electron beam that are reflected back. By contrast, secondary electrons originate from the atoms of the sample. Because backscattered electrons come from deeper regions of the sample and secondary electrons originate from the surface, the two deliver different types of information upon reaching the detectors. Finally, a three-dimensional image of specimen is formed on a TV screen. The field of microscopy has been constantly evolving over the years. We have the development of various microscopes like confocal microscopy, in which by altering the focal length, different focal planes of the specimen can be viewed and imaged. To understand this better, a simple example. Unless we cut open a multi-layered cake, we cannot see what is there inside it. But by using a confocal microscopy, it is like without cut opening the cake, we can see what is present inside. It's just an analogy for your understanding. Majorly, confocal microscopy is used for protein localization studies. The cryo-electron microscope, which allows the user to image cells, organelles and also the macromolecular protein complexes, is an advancement. The scanning probe microscope has revolutionized nanotechnology. It allows images of surfaces and structures, including atoms, to be captured at a nanoscale. There are various types under the scanning probe microscopy, like the atomic force microscopes and scanning tunneling microscopes that are high-end microscopes providing a resolution of up to 0.1 nanometers. Let's recap today's session. Microscope is essential for viewing and studying specimens too small to be viewed with naked eye. Robert Hooke and Antony van Leeuwenhoek have made astounding discoveries of the cell and animalcules by using microscopes. Microscopes use convex lenses and their working is governed by resolving power and numerical aperture. There are two main types of microscopes, mainly light and electron microscopes. We have studied the different types of light microscopes like bright field, dark field, phase contrast, differential interference contrast and fluorescence microscopes. Electron microscopes are more superior and include two main types, transmission and scanning electron microscopes. We have also seen how the field of microscopy has evolved over the years so that now we can image even at the molecular and atomic level. That's all for the session today. I hope you all see, enjoy and appreciate the fascinating microscopic world. Thank you.